Hi everyone. In this video, I want to prove the Gauss-Bonnet theorem, which is one of my favorite theorems of all time, and I find it exceptionally beautiful because it establishes a connection between a curvature, which is to be thought of as a local invariant, and the Euler characteristic, which is a global topological feature of some space or manifold. So I'm going to talk about some generalities first before setting up this theorem, and then we're going to prove it. First, I want to establish a couple of facts that we're going to need in the proof. So there's going to be like Sard's theorem, critical values, then we're going to talk about the notion of volume forms, degree, the main result regarding these, curvature and the Gauss map, and then finally we're going to prove the Gauss-Bonnet theorem and Poincare-Hopf theorem, which is also very beautiful. So to start, I'm going to let x and y be smooth manifolds. And this theorem of Sard states that if F is a smooth map between these manifolds, then the critical values of F have measure 0 and y. So this shows that being a regular value, that is to say not a critical value, is a generic property. Most points in y are not going to have the property that they're the image of a critical point, where the rank of the derivative, which is a map between the tangent spaces, is less than full rank. So it's usually going to be a regular value. Then this is something that operates in a high degree of generality. In fact, Smale proved a generalization of this to infinite dimensional Banach manifolds. So this is really a surprisingly strong and beautiful theorem that gets us quite far in the realm of manifolds. Now I will reduce to the situation that we'd be interested in, which is that now take x and y to be compact and oriented and manifolds, so of the same dimension. So none of these assumptions were needed for Sard's theorem. You can have non-compact, non-oriented, manifolds of different dimension. But when we have this map of compact-oriented K-manifolds, when I say map, it's implicitly smooth map, unless I say otherwise, which is probably never. So if F is a map between two such manifolds, then because we're oriented, we can define the oriented intersection number, or the degree of F, which is the intersection number of this map F with for any y, let's say for any regular value y. So this degree is independent of the choice of point and expresses the number. Essentially, it says that F looks like a covering map of its given degree between x and y, or at least locally so. So then the crucial invariant regarding integration of pullbacks of differential forms and the way this interacts with the degree is the following. So we have this theorem. Again, setup is going to be like 90% of this video. And so we're going to see how beautifully and simply we can prove the Gauss-Bonnet theorem once we've set up all the right generalities. So if f from x to y is smooth, under the assumptions above, compact oriented, same dimension, and, yeah, let's say same dimension, and omega is an n form, a differential n form on y, then we can pull back a differential form via a smooth map to yield a differential form on x. And this process is called pullback and is denoted f star v. F star omega. Then it turns out that the degree of f times the integral of omega is equal to the integral of the pullback. So when you're integrating the pullback of a k form, this is going to be, an n form, then it's going to be the same as the integral of the form on the original manifold, on the target, up to the factor of the degree where you're kind of treating it with this multiplicity. And the idea is that you prove the statement locally. So you take around each regular value, you take a neighborhood, then you take the preimage of this neighborhood under your map, which locally looks like a covering map. And so you have some disjoint open subsets in X, and each of these are diffeomorphic to this neighborhood of a regular value. So each of these occurs with a positive or negative index, depending on whether this map is locally orientation preserving, that is, whether it preserves orientation on each of these stacks that map to this open subset. And then you can cover the complement of the critical locus by opens and then use a partition of unity. So it's a local statement, and we can see how it interacts with orientation. So I'm going to work with manifolds immersed in Rn, embedded in Rn, let's say. By Whitney, this is fine, and Gauss-Bonnet in our formulation is just going to apply to hypersurfaces, so no harm done. But importantly, being embedded in Euclidean space allows us to inherit a canonical volume form, which is what we are interested in. So a volume form, in general, is an element of the top de Rham cohomology, non-vanishing element of the top de Rham cohomology. So if, let's say, x to the little n is embedded in R to the big N, then we have a volume form, let's call it nu x, on x assigns to each x in X some k-linear map on, n-linear map, I keep getting confused, some n-linear map on the tangent space. Some on this, such that when you evaluate this thing on a positively oriented orthonormal basis, this returns 1, so it's got this normalization property. Basically, it takes in an n cube, right, an n cube that's positively oriented and with unit sides, and it spits out the density, which is equal to 1. So this is what this differential n form is doing. So if v1 through is orthonormal positively oriented basis for the tangent space. Okay, so now if we have any other ordered basis, then this thing, when you evaluate it on some other basis, is going to transform by a factor of the determinant of the change of basis matrix. And in particular, we say that the volume of X is the integral, the integral of this volume form, which is reasonable because you have this measure that at each tangent space takes in a unit hypercube and spits out 1. And so if you want to add these all up across your manifold you're integrating, then at each tangent space, each of these should contribute a unit amount. And when you add these all up across the points, then this should spit out the volume in any reasonable sense. So this is the volume of our manifold, and this is an important quantity that we're going to be interested in. And we're going to connect this to ideas like curvature in the Gauss-Bonnet theorem and the Euler characteristic. So if we have a diffeomorphism, then the volume form is actually not preserved, but it can squish or change up to some factor. And depending on the smooth map, we associate something called a Jacobian, which actually agrees with the usual Jacobian for Euclidean space, for example, that measures the extent to which this volume form gets distorted. So we want to measure the distortion of volume under a smooth map. So we come up with the following definition. Now, if f is a smooth map from x to y, where these are compact oriented, then we define the Jacobian to be a map from x to r also defines, so this is not confused with like a lemma or something. So we define this with the unique property that the pullback of the volume form on y via f is j of f times the volume form on x. So it's measuring the extent to which this volume gets rescaled. Because this j of f, right, when you're pulling back this volume form on y, then you want, because you're working in top degree cohomology, this thing is a one-dimensional vector space, and so nu x and nu y are going to, or nu x and the pullback of nu y are both going to be n-forms. Then we want to measure their ratio, which is going to measure the extent to which the volume gets dilated or contracted, and then j of f is exactly this function that we're defining, or this number that we're defining, based on f that returns the scaling factor. So in local coordinates, this is just the determinant of the Jacobian in the usual sense. So now we're going to talk about curvature and the Gauss map. So let x be in Rn plus 1 be a codimension 1 hypersurface. I will say this discussion can be carried out for Riemannian manifolds, where we have the notion of a metric connection, but in this case we have a canonical connection that's given by a submanifold in Euclidean space having a Riemannian metric inherited, the Euclidean one. So we can generalize this a bit, but this is the situation that we're going to cover in this video. So if we have x to be codimension 1 hypersurface, compact, oriented, etc., orientation as a submanifold of Euclidean space of dimension r, n plus 1, we have a natural map that to each point is going to give the direction of the outward unit normal. So it's going to send each x to direction of outward and this is going to be some unit vector, so in fact it can be seen as an element of the n-sphere. This is called the Gauss map, I think, for historical reasons. Gauss was tasked with making a faithful world map, so this was the genesis of some kind of mathematical cartography, and he realized that you could never do this without some kind of distortion happening, and this is due to the positive curvature of the Earth, whereas a map is flat, so it has zero curvature. Then there's no way to faithfully represent, in an isometric way, distances and angles on a globe. And so this Gauss map is capturing the idea that you're somehow wrapping this codimension 1 hypersurface around the n-sphere of the same dimension. And so when you're mapping each point to the outward unit normal vector, then you're just looking at the direction at which it's pointing as an element of the n-sphere. So then we're going to use this to define the curvature, because we're going to compare it to the curvature of the n-sphere. And if we think of the sphere as having constant curvature 1, then the curvature is going to measure the extent to which this distorts for some hypersurface x. So we define the curvature kappa of x at a point x, so it's a local phenomenon, as the Jacobian of the Gauss map in the sense that we're looking at j of n at x. Okay. And remember that j of f is going to be a function from x to r, so this is something that depends pointwise. Okay, so as we've mentioned, spheres, that is a really bad sphere. Let me try to use the drawing tool. So spheres have constant positive curvature in, let's say, R3, then a flat plane has constant curvature of 0, and let's say, let me try to draw this in a reasonable way. A hyperboloid is going to have, oh dear, that's fine. Oh my god. Is going to have constant negative curvature. Okay, that's good enough. But you can have examples of manifolds that have non-constant curvature at different points. It just happens to be that these things have constant negative, 0, or positive negative 0, positive constant curvature. So now we are ready to set up the Gauss-Bonnet theorem, which connects curvature, which is a local invariant that depends on points on your manifold, the extent to which volume is stretching or rescaling, to the Euler characteristic, which is a global invariant, which is related to the number of holes, the genus, and is a purely topological invariant of your manifold. So let us state the theorem. If X is a compact orientable and manifold, without boundaries, let's say closed orientable. And n is even, and we have the following beautiful formula where when we integrate this volume, the curvature against the volume form, we have 1/2 times this constant, which I'll explain in a second, times the Euler characteristic, where this is equal to the volume of Sn, and chi of x is, of course, the Euler characteristic. So before we do this, we're going to need one more theorem, which is called the Poincare-Hopf theorem. So this is what I view as really the driving force behind Gauss-Bonnet, to be honest, because it is the first instance in differential topology of a truly local to global principle, where you're looking at a vector field on a manifold, closed manifold, let's say, and the information about its zeros is somehow connected to the global topology of the surface, or manifolds. So we need the Poincare-Hopf theorem. If V is a vector field on X with isolated zeros, then the sum of the indices at the points are 0 for this vector field, right? Is the 0 vector at each of these x's. If you add these all up, then you get the Euler characteristic. And so index, I'm not going to go into like a formal definition if you're not familiar, but the idea is that sources and sinks of vector fields should have a +1 index, and saddles have -1. So in some sense, it's measuring the local behavior of a vector field. So I'll give an example. That's not. So let's say we have some n torus, or let's say G torus. Then we have that by this theorem, we can form this following vector field. So we're going to go around each of these. So we have one source, one sink, and then for each of these, there's a pair of points around each hole so that we have a saddle. So we have 2 times the number of saddles as we have holes. So the number of saddles is going to be 2g. So this contributes -2g to the count by Poincare-Hopf. And then one source and one sink at each end of this manifold of genus G is going to contribute 2. So we have 2 minus 2g, and this gives us the following classical relationship between the genus and the Euler characteristic. So this is a really useful theorem. And index of vector fields, this is a sum over local invariance, and then we have this global thing, which is the Euler characteristic. There are fairly sophisticated ways to view this. Like you view a vector field as a section of the tangent bundle, and then you're looking at the Euler class of this tangent bundle, and you evaluate this on the fundamental class of your manifolds, and so on and so forth. But I won't talk about the very highbrow perspective here, even though there's some nice resources which I might link. Okay, so now we have established Poincare-Hopf, which is this local global principle for vector fields, and we can prove the Gauss-Bonnet theorem. So proof of Gauss-Bonnet. We have that the integral of the curvature with respect to this canonical volume form is just going to be, by definition, the Jacobian. You integrate this Jacobian of the Gauss map with respect to this volume form. This is how curvature was defined. But then we note that this is just, the volume form is just the pullback, right? So this is the Jacobian. This is the factor by which we're scaling when we have a diffeomorphism. So this is just the pullback of the volume form. Oh, sorry, this should be on Sn. So we're integrating the pullback of the volume form on Sn via the Gauss map on X, which is the source. And by the degree formula for top forms that we looked at earlier, this is just the degree of n times the integral of the canonical volume form on Sn. But now recall that we defined the volume of a manifold to be the integral of this volume form. So this is volume of Sn, but in our notation, this is just gamma n. So now it remains to show that the degree of the Gauss map is equal to 1/2 of the Euler characteristic of X, i.e. 2 times the degree of the Gauss map is equal to the Euler characteristic. Okay. So we want to find some kind of suitable vector field on which to apply Poincare-Hopf. So we are going to do the following. So apply Sard to the Gauss map from X to Sn, so we can find some point, I'll call it A, in Sn, such that plus minus A are both regular values. Then if we couldn't do this, then this would violate Sard, because then the regular values would not be the complement of a measure zero set, right? Then they themselves would have measure zero. So now we have these antipodal regular values. I'm going to draw this on the n sphere. Oh dear. Let me say this point and this point, which you want to imagine on the other side. This is A and this is minus A. And we have this map from some manifold, closed oriented manifold. Here to Sn. So I'm drawing everything in R3 just to visualize. And now we're going to define a vector field V, that looks too much like nu, V on X, such that the value of this vector field at each point is the projection of each A onto the tangent space at this point. So now we can ask ourselves, what are the zeros of V? Well, the zeros are exactly those points for which the tangent space is going to be orthogonal to A. So this is going to be the locus of points here such that this is orthogonal to the normal vector at this point. But this is equivalent to saying that these are exactly the points for which n of x equals plus minus A. So the zeros of this vector field are exactly those points that map to these antipodal regular values. So because these are both regular values, then the preimage of each such is going to be the degree of the map. So then the preimage of A is going to consist of degree of n points, and we also have negative A, so we have 2 times the degree of n, and by Poincare-Hopf, we have the zeros of this vector field, of which there are 2 times degree of n, is equal to the Euler characteristic. And so we're done. It's a proof that I find lovely, to be honest. All these elements coming together in such a beautiful way, constructing this vector field, using Sard's theorem to find antipodal regular values, and then concluding that twice the degree of the Gauss map, which is the fundamental function that we're interested in here, is actually the Euler characteristic. So this shows that this global property, the Euler characteristic, which is invariant under diffeomorphism, is actually related to, up to some kind of scaling factor, the integral of curvature, which depends on the local geometry of the manifold. So this is not a priori clear. One small thing we can ask, I'll just say this out loud, what goes wrong when n is odd? We remember that we said this proof works when n is even. Then the sum of the intersection indices for these antipodal points, so the degree of the antipodal map is 0 for even n. It's not so for odd n. So if we have opposite points, then they cancel each other out for even n. But then the antipodal map reverses orientation, so we don't get this kind of cancellation when n is odd. Yeah, I think that's all that I have for this video. Thank you for watching.